So if you happen to watch one of my videos a couple videos ago, I made these soft jaws for my 4-jaw chuck for an upcoming project that's going to be rather involved. And one of the things I noticed at the end was that the placement of the magnets to hold the jaws on was the top surface of the jaws, and that's a hardened ground surface that you can use as a reference. If you've got a part with a flange, you can slide it up to it. So I am going to make a new version of these jaws where instead of having the magnet here, the magnet will be along the side, and it will hold the jaw in place without interfering with this surface. In order to do that, I'm going to modify my dies so that they can reference off of this wing that's going to stick off of here. Also, since I'm going to be using the dies more, I'm also going to heat treat them, but they're made out of 1018 steel, which is only 0.18% carbon, and that's not enough carbon to really heat treat adequately, or even really at all, I think. So what I'm going to have to do instead is surface harden them, or case harden them, with some case hardening compounds, so I'll be doing that too. And as long as I'm at it, I'm kind of curious, because these jaws are moving, they move along a what do you call it, a little rail, and you know, I'm kind of curious how much they can't when you tighten them. So I'm going to put a part in this 4-jaw chuck and do some measurements and see, you know, how flat this surface really remains when you're tightening a part down, or can you really count on it if you're trying to do precision work. So hope you find that interesting. Let's just get to it. So I stuck a part in here and centered it in the 4-jaw chuck. So the next thing I'm going to do is grab another indicator and put it on these flat faces and first see how well they line up with each other once it's tightened. I assume that when they made this in the factory, they tightened all these down on something or maybe on themselves and then ground them flat to each other. But you know, once you throw a part in, that, you know, how well that stays flat along the travel of each jaw is an unknown here. And then also I want to tighten just one jaw and see if it cants at all, because this rides along a track, and although the threads are engaging, you know, much of the bottom of this jaw, in reality screws, when you tighten them, a couple of the threads hold the majority of the force and the other threads are looser. And if that's the case, this might cant a little bit, and I want to see if that's the case. So let's throw another indicator on here and see what we see. So even though you know, these jaws were likely all put in the chuck, tightened together or tightened on some reference part, and then ground to be that they only became flat at that one instance. And in reality, it's not terribly repeatable, my guess, because here's 0 on the jaw. You'll notice across the face of the jaw it varies by 1,000th. And as I come to the next one, it's plus 1,000th, doesn't reach the 0 at all, goes to plus 1.5 thousandths. And this one is minus 1.5 thousandths, going to 0 on one edge, and then plus 1 again, and then back to the original jaw. So, I mean, I see a 3,000ths range. So if you're doing ultra-critical work, you really cannot rely on these surfaces as flat. Now, let me change my setup here, and let's see what happens when you crank on one and see if the jaw cants at all. And maybe, in order to get this right, just throwing it out there, like tailstocks, when gunsmiths are going for ultra-accurate tailstock alignment, they will use a torque wrench to make sure to tighten the tailstock to get a repeatable measurement set up every time. So maybe you have to, if you need ultra precision work, which I've never done and have no experience with, maybe you have to have a chuck, maybe a better chuck than this one, but on top of that, maybe you have to have a chuck that you can apply a known force every time, like either through a torque wrench or a hydraulic chuck, where everything is controlled with more precision for repeatability. Anyways, let me see if the jaw is cant at all. I'm going to change this up, bring it right back. So I've loosened the jaw, this top jaw here, and it was set at 0 when it was tight. So we are down 2.5 thousandths, and as I tighten it, you can see there, I think I bumped my 0, but the jaw does cant. So here is tight, really tight to really loose, and it's like 2.5 thousandths of change. So the moral of the story here is jaw pressure does affect how flat this guy is, and so it probably becomes important if you're doing precision work not to rely on these surfaces, especially if you can't guarantee you're going to apply even force on all the jaws. All right, so let's go make our, modify the die so that we can make the new soft jaws. So as far as modifying the die is concerned, I am going to be taking a 1/2 inch off this ridge on the bottom to allow a reference point for the unbent part to slide into, and that will allow room for the wings to extend out the edge that are going to wrap around the side of the jaws. So next stop, the mill. Maybe I'll do one side at a time here. Next up, before I actually make the new soft jaws, I want to case harden or surface harden the die and mold, and because this is cold rolled steel, it's very low carbon content and it's not hardenable on its own, so you have to use a product like cherry red in order to case harden it. And what that does is you heat the material up until it gets to a point where carbon will dissolve back into the steel, and cherry red provides that carbon. It also provides a protective coating on it so it doesn't oxidize, so you don't end up with a thick oxide layer. But I'm kind of curious, the normal method for using cherry red is you heat your part up until it's cherry red, thus the name, and you either sprinkle or dip the part in some cherry red, and it will form a molten black coating on the surface of the part. Then you heat it to cherry red again and hold it there for a while, and then quench it in water. Now I'm curious, because that initial heating you do before you put the cherry red on it, I think it's going to expose the part to some oxidation. And I don't know if the cherry red has additional compounds in it that help dissolve the oxidation, remove it. I've never used it before, so I have no familiarity. But what I'd like to do is try using it in two separate ways. What I've done is I took a piece of this cold rolled I've got that's cut off, a little cut off piece that was stuck under my bandsaw, this piece right here, and this was one single piece. And what I'm going to do is I want to measure its dimensions, its thickness. I also made the surface fairly smooth and polished, because what I'm curious to see is I want to treat this two separate ways. The first piece, I'm going to case harden following cherry red's normal instructions. Heat it up to cherry red, dip it in the material, heat it again, quench it, and see what it looks like. The second piece, I am going to take this stainless steel box, and I am going to take the part in the stainless steel box along with these parts, since I want to do them the same way. It may make no difference, but what I'm going to do is pop this in the kiln, put cherry red all around it so that it's completely coated in cherry red, so that as it's coming up to temperature, it's coated in cherry red right off the bat. Hopefully that'll reduce oxidation. Maybe I'm curious to see if that'll change any of the dimensions. I'm also going to measure hardness on both these parts to see if it's the same. One thing I won't do, because I don't see I can do it quite easily, maybe, would be to see what the depth of hardness is. Maybe take a pass with the milling cutter and then measure hardness and really light passes and see when the hardness changes dramatically. I don't know if I'll do that or not. But I would like to see about dimensional changes to see if there's oxidation differences. So these two pieces came from the same piece of metal, and I finished them so that they were accurate to within less than 1,000th thickness of each other. So I'm kind of curious to see if the two processes will yield different results. I know that when you harden material, like in steels that are hardenable, the dimensions do often change because you're changing the crystal structure in the metal, and so the individual atoms aren't in the same positions as before, and so you can get differences, which is, what you expect. Tool steels like A2 are chosen specific alloys so that the changes are smaller than other tool steels. And the trade-off often is hardness or toughness or abrasive resistiveness. So anyways, I'm just going to experiment with this and see what the results turn out. The end result is I still want to use the die and mold, you know, in the traditional sense to make the next set of soft jaws for my chuck. I know it's a long-winded explanation. I just wanted you to know where I was headed from here and what my thoughts were. So let's just get to it. So before we get started with the heat treating here, I have labeled the two blocks A and B. I don't know if you can see that. Then on the backs of them, I noted the X direction and the Y direction on each one. And I took down some figures, and what I did was I took the thickness in the middle of each of them twice and made sure I got the repeated value. I took the thickness in the X direction, the thickness in the Y direction, and the rough Rockwell hardness of this. And I used Rockwell C because that's what I had calibration blocks for. Probably would have been better to use Rockwell B for this unhardened material because this probably, you know, that's towards the very end of the scale, and so my hardness meter probably is not as accurate there. So we're going to come back. We're going to start by taking A, and we are going to heat treat that in the traditional cherry red fashion, which I previously explained, and take some measurements. And then the other side we will put with the other two parts, and I'll use my kiln instead. So here we can see a close-up of block A before heat treating, and the surface has scratches in it, but other than that, doesn't have any divots or anything like that. Fairly smooth surface. There's a hole I drilled to hang it while I'm heat treating it. Alright, so we're going to try and catch this on camera. Hope it's successful. It's going to be kind of hard to do to fit it in the image. So, let's get our torch heat up here. So, also wearing welding goggles, it's going to be kind of hard to try and get this guy to red hot, cherry red. We'll find the words. Alright, I think we're there. We're going to dip, coat as evenly as we can, and then go right back to heating. So the stuff melts, forming a protective coating, and I think maybe even removing oxidation. And it's cherry red right now, and we'll quench it. And that should be it. We'll take some measurements. Hope you could see that. So here's what it looks like after it's been quenched. I don't know if you can see it, but the material is kind of hardened onto it. The material just feels different right off the bat. So let's take it over and take some measurements. Hi, so here we are after the first case hardening process, where we followed the standard cherry red process of heating it to red, etc., etc. The dimensions were interesting. The dimensions changed from 0.228 thickness to 0.227. The x-axis increased by about 1.5 thousandths, 2.5 thousandths. The y-axis increased by 2 thousandths, and the Rockwell hardness went from approximate Rockwell C3 to Rockwell 62.8. So the depth of the case hardening is probably pretty low, and what we will try to do next is case harden this guy. So we've loaded all the parts in the stainless steel box I made, put it in the kiln. We've set the program to ramp up to 1450 Fahrenheit. hold for an hour to give it time to soak all the way through. That's sort of the general rule, an hour per inch of material, and some of it's about an inch thick. So we're going to do that, and we've covered all the parts with the material. We're wasting a whole lot more of the cherry hard than we'd need to if we were doing the dip method. I'm just curious if this is going to help reduce oxidation. So next, we're just going to start the program, and we'll be back. All right, so we're ready to do this. We're going to pull this guy out. Holy cow, is that hot? And so you're probably wondering what just happened there. What actually happened was everything was going fine with the Quench, except that the container is shaped like a box, and everything was fine as the water level came up the sides until the water went over the edges of the side. Then the water hit all of the super hot parts, heated from all sides simultaneously, and exploded, blowing water and cherry red debris all over the place. Thank God I was wearing safety glasses and clothes, but still, stupid, and I was very lucky. So here's the parts after case hardening, and I took this to the Scotch-Brite wheel and cleaned off some of whatever this layer of stuff is here. It comes up, it's pretty hard, whatever it is. You'll notice the interesting patterns in it. Looks like some of the material got lost, like it almost scaled or partially melted. Kind of interesting, considering the kiln was set to a very fixed temperature. But you can definitely see it, and it is very hard. I'll be interested to see how deep it goes. So I'm going to take some polishing stones to this to polish the mold or the die part of it. And this guy needs a bit of work still. I just left this. You can tell this is where the material came off, and here's where the material, the cherry red, stayed on the whole time. And it's very different than the way the other one looked. It did protect the metal, which is kind of interesting. Here is the little sample piece, and we can compare. This one was completely buried, and you can see that it's the metal's a lot better protected. So it finishes pretty nicely, and it's pretty darn hard. Interesting, I just went straight across there. You see, this is the area where the cherry red was completely covering the metal the whole time. Here it was not. Here you can see, when I take it to the Scotch-Brite wheel, the damage, the oxidation is on the part that didn't have the cherry red on it. The other part it cleaned up really easily. Like this side was mostly perfect. It was white like that, and you can see that it cleaned up pretty nicely and easily. This side had a little bit of issue still, and it did not. Very interesting. So here's a close-up of that same part I was just showing you, and you can see there's plateaus and valleys and all kinds of stuff. Especially here's crystals, and it's all over the place. This is the part that wasn't protected, and it's interesting, the part that wasn't protected has all these little crystals growing on it. I wish I understood the metallurgy better. I could tell you what they were, but I can't, unfortunately. And here's an even closer view of the part that was protected, and you can see all these little pock marks and divots and holes. The case hardening process is really kind of hard on the surface metal, and I'm guessing that something gets dissolved and removed while the other material gets hardened, like maybe carbides or something. I don't actually know, and I'm just sort of throwing it out there, but it is very interesting to see. Next up, we should see what the measurements are on our test piece. Looking at the measurements of the second test piece after the modified case hardening protocol, where I heated it in the oven, the dimensions were sort of stable as well, just like the other one. The thickness went from 0.2277 to 0.2273, and that kind of 4/10 error could easily be just taking the Scotch-Brite to it, changing the difference. You know, that's almost nothing. The x-axis changed a little bit more dramatically. It went from 0.993 to 0.957, and the y-axis went from 0.971 to 0.973. So a couple thousandths increase there, but a lot of loss in the x-axis. A little bit different than the other one. It was much easier to clean this guy with Scotch-Brite. The hardness went from about a Rockwell 3 to a Rockwell 57, which I thought was particularly interesting considering the other one got harder. And I went back and rechecked them again and came up with the exact same numbers. So for whatever reason, the second process, not quite as hard. And you know, I think that might have to do with the quenching, because the faster you quench it, the harder it'll be. The first one was just this tiny little ingot dropped in a lot of water. The second one had the water exploding all over the place, so the water didn't remain in contact as long, so it cooled a little more slowly, and that's probably explains this, just guessing. I'm really kind of curious about the chemistry involved in this. Unfortunately, they don't give any information on the Cherry Red site. And I don't know, there's potassium nitrate and there's chromium oxide in it. There's no carbon source at all as far as I can tell, unless there's, you know, the MSDS doesn't list the carbon source. So it makes me wonder, are they actually adding chrome to the metal to make the outside hard, kind of like one of the chrome edge files that they used to sell? Anyways, I'd love if someone knew what the chemistry of this was to let me know. So I've mounted my two test samples, A on the left, B on the right. A being the one that was case hardened normally, and the one on the right more deeply, I'm guessing. I'm hoping my carbide inserts will hold up to the hardness of these parts. May not. So I'm going to take like 2/1000ths pass across the top of this guy. And so we know the hardness of these two right now. This is a little over 60, and this one's like 58. So I'll take a pass, measure hardness again, keep it up until I start to find a discrepancy, and let's see what the difference in the depth of case hardening is for, you know, like a 1 minute exposure to the case hardening material, and, you know, about 2 hours in total, but an hour at temperature. All right, let's do this. I will say these really hard materials give a great surface finish. All right, let's measure some hardness. All right, so here is the A block. Starting to fall off. And the B block is staying pretty hard, only down a couple points. The A block is down a few. So let's take another pass and see what we get. Let's take another, say, 4/1000ths and see if we completely break through on the A block. So the one that I thought would be most deeply hardened actually has lost all its hardness about 10 or 15/1000ths down. The one on the left appears to have held it better, which is really interesting. I don't even know why that is. I can't begin to explain it. But yeah, it seems to have held a bit more of its case hardening than the one on the right. You'll notice the finish has gone to hell. That's because the material's so hard it's damaged the carbide already. So a little surprising, and I can't explain the reasons why, but measuring repeatedly seems to come out that the one on the right is almost down to base material softness, and the one on the left has still got a bit of hardness. I don't know why that is. So I know the point of this exercise was to make soft jaws for my my 4-jaw chuck and my lathe, but in reality I was more interested in how the heat treating was going to work and how the case hardening, how effective it would be. I learned a lot in the process. I tried a couple variations. Originally I was going to have a long tail sticking up on one side, that's why I milled the bit, and I didn't really like that. I don't think the magnet will have enough drag to really keep it in place adequately. There doesn't need to be a lot of force, but it tends to move around anyways and attract a lot of iron filings or steel filings if you're doing steel. So I think it's going to work out just to do the style that is friction fit like this. And interestingly enough, I can just reload it in the die when it stretches out when I use it in the vise, and reform it, which is kind of cool. I thought about this variation where I'd punch some holes in both sides, put pins in here, and use rubber bands, and it holds on really nicely, but I'm a little concerned that the coolant or lube will dissolve or weaken the rubber bands, or when they break, you get those little pins flying off. Now, I wear safety glasses, but still, you don't want flying objects. You don't want to plan that into your design. I learned a lot on this design, this project, about the case hardening, and certainly what not to do when you're quenching. If you have a square box container or even a hollow cylindrical container, if you dump that in, not other than sideways, so that the outsides, the water creeps up equally along the outsides and then dumps into the middle. When it dumps into the middle, it'll flash evaporate, and it'll cause a lot of pressure pushing to the middle. So all the remaining liquid in the middle has only one place to go, and that's up, which is what happened. It basically blew water and debris all over the place. So that was a really harsh lesson, and I got really lucky, and I'm thankful for that. Hopefully you will learn from my mistakes and not duplicate it. I will keep playing with the variations on this idea and see how they turn out. I'm kind of curious if there's a better solution still for the soft jaws. I haven't run across it. So I've watched other people's videos as well, and they tend to do the form-fitting design in several variations. Sometimes they curl around the back. I could play with that as well. Once I've got this design, I can just keep pressing them out. Thanks for watching. Hope you found it useful. Hope to see you next time.